in variational methods, we are very much used to, oh, how nice it is to have chalk and blackboards. So in various cases, we want to estimate some signal, which is the true signal. And this can be a signal or an image, or whatever you want to estimate. And you are having some noisy version of it. So you have the data, which is an Sn, which is true, and then you have the noise. And then what we do most of the time is we do the following thing. We define that the best estimate of the true signal is the argument that minimizes over all possible s's some distance between the s and the s noise. This is some measure of closeness plus some lambda times the distance between s and some prior information on S true. It's not always exactly this written in this way, but this is what we have. And what is happening is that this prior on the S true very often is given to us as the S true is smooth. Okay, so this is an example of a prior information that we could have. And then what we want to do is we want to define this distance to smoothness, for example, by integrating the derivative, okay, or the gradient of this. And that is sort of the regularization term. That's called usually the regularization term. Now, what happened is that some time ago, I had a student by the name of Tal Nir who was doing, with whom we were looking at the problem of optic flow. And when you look at optic flow, you want to recover signal. The signal is the u and the v vectors. They are a pair of vectors that define the local optic flow vector. And you want to recover it from the data, and you do all kinds of things, and then you recover a u field and a v field, and this is what you do in the optic flow. Actually, we have seen in the last example of the previous talk, you saw the optic flow in action for one of these moving images for video processing, and it's a very nice topic. But then Tal Nir once came back to me and said, you know, when we have this optic flow, usually what is producing this optic flow is rigid objects that are moving in the image in some way. And of course that is true when the world is static and you just take your camera and move it. Okay, so the world is presumably roughly rigid. Now, rigid optic flow has a very strong algebraic structure. It is not any u and v any pair of u and v fields that can give rise to rigid optic flow. It is parameterized. It is parameterized by the rotation, by the 6 parameters that we have, and so forth. So, in fact, what you have is often you have for the true thing that you want, you have some sort of parameterized model. Okay, so this S true can be in fact S of some A and B and C and some series of functions, okay, which are parameters which when you know them you can say what is S. Okay. So now what Tal Nir told me, okay, let us put these parameters, these A, B, and C into into the formula. And then what we are going to do is we are going to do the following. We are not going to recover S anymore, but we are going to recover A, B, C, and so forth. And here we are going to recover A, B, and C, and so forth. And here we are going to do the argument, the argmin on A, B, C, and so forth. And we are going to estimate not S, but some A, B, and C. And here we have to do not prior on the S true, but prior on A, B, C, and so forth. Okay? So now, wouldn't you throw out a student that comes to tell you this? Of course you would. Because you, instead of optimizing for one function or for two functions, now you want to optimize for 6 functions. Okay? Okay, it looks absurd. This is the over-parametrization idea, okay? Okay? This is the over-parametrization idea, and the question is it good? Is it any good? I mean, does it buy something? Well, it turns out that for the optic flow, it did very well, okay? It performed very well. So it gave you a very, very good, optic flow system, and I am more and more convinced that this idea deserves more and more elaboration and more research, okay? So in the meantime, we did some things. The big problem was that now, instead of having a prior on your signal or on your image or on your data that you want to recover, you have some prior on the behavior of these parameters. So you might know that, for example, that these parameters are constant. If you know that these parameters are constant, then this whole thing becomes a simple optimization problem looking for a constant vector, okay? That's very nice. But if you know that they are functions that you allow them to be functions and of time or space or so forth, then everything becomes much more complicated. And this is where another idea that was running around came into place, and this is the idea of sparsity. Suppose that we know about the A, B, and C's, that these are functions that are varying in time, but they are varying in time in such a way that they change, that they are piecewise constant. Okay? So they are constant for a while, then there is a jump. They are constant for a while, then there is a jump. They are constant for a while, and there is a jump. So in fact, what you are trying to recover is you are trying to recover A, B, C, D, and so forth parameters which are piecewise constant, and these piecewise constant functions jump in unison at some locations which you don't know. Okay? So what you know is you know about these parameters that they are jumping from time to time, but you have to sort of locate these times, and you have to sort of evaluate what will be the new constants in every interval. Okay? So now the question is, in a variational procedure like that, the question is, how do you actually impose this idea of piecewise constant and jumping in unison? Okay, well, when a signal is piecewise constant and jumps from time to time, rarely, what you know is that its derivative is 0 almost all of the time, and it has only a few delta functions, okay? So, in fact, you know something about the sparsity of its derivative, okay? So therefore, sparsity is coming in as part of a signal model. So that is how the marriage between over-parametrization and sparsity, in my opinion, will lead, or already led to, and will lead to some nice results. So let me do the following. I'm going to tell you a little bit about sparsity because This sparsity is reviewed in this paper, but I'm going to give you, my talk is going to concentrate a little bit about sparsity and about over-parametrization. So let me show you what will be the overview. So in sparsity, we are dealing with the following problem. You have a linear system, and the linear system is underdetermined. And what you want to recover is you want to recover this vector xm, this vector x with m entries, and you have only n with n smaller than n m equations. Well, this is a highly determined system, and therefore you have many solutions. So the question is, how do you choose from among the many solutions? Well, you define a measure of the desirability of the solution, and then you solve, instead of that linear system equation, you solve a minimization problem of this sort. Okay, and then you have various types of measures of desirability, and in fact, a big splash came when the L1 norm started to be used in signal processing in the literature, and L1 norm was found to be related to the L0 norm, which is the number of non-zero entries in this vector. Okay, so now the paper that I was referring to in the first slide surveys the wonderful results that the community has managed to produce about sparsity, about various conditions for the equivalence between the J0 and the J1 norms. And in fact, you can prove results of the following kind: that if the signal, or if your vector is sparse enough, it means that it has the number of non-zero entries is smaller than a certain threshold, then both J0 and J1 will give you the optimal solution, the same optimal solution. And this was a revolution, because J0 involves an exhaustive search, which is absolutely unfeasible, whereas J1 is solvable by linear programming. Okay, so this is something that is very nice, and it has to do with some conditions on the matrix A, and I don't want you to even try to figure out what are exactly these conditions. And then there were some further messages that you can actually find out what are these models. So you have a KSVD type of procedure to recover the matrix A, and I don't want to go over these things. But what I want to tell you is, I want to tell you the following. I want to tell you how this notion of sparsity came about, and at least came about to me in the field of signal processing. And then I want to tell you about the over-parametrization variational methods that Tal Nir originated in this optic flow paper. And then I want to tell you a little bit about moving least squares, which is, and about a very old paper by Savitsky and Golay. And this is always very nice to look at old literature, because you might find beautiful gems. And then I'm going to tell you how recently we used the two fields and combined them in order to come up with something which is reasonably practical for over-parametrization variation methods. However, the message is that a lot needs to be done still. So let's start with music and echo resolution. So suppose you have a medium, and you probe this medium by sending into it a signal. The medium is going to send you back some signals. Schlumberger? Somebody from Schlumberger? They do this all the time, okay? So they are sending a signal into a medium, and the medium is sending back some signal r of theta. Now, suppose that you have this signal r of theta that is composed with versions of the signal that you sent in, which are delayed at various locations, okay? And they are also multiplied by some random gains. So you send in a signal, a pulse, and you are getting back a series of pulses after a time, and presumably this is how radars work and things like this. So now sampling this r of t at n points of time is giving you the following set of equations. Okay? Now, if you define a of theta as a of t minus theta, the sampled signal at a delay of theta, then this could be expanded into a huge and very, very large matrix, listing in the row all the possible finely discretized values at which the signal could come back at you. And here, this signal could be made into a very, very sparse set of zeros with rows, with row values, with these random variables located at the places where the signal actually came back, okay? So here it is. This is a problem of the kind that we discussed in sparsity. So we have like a sparse vector with only k non-zero entries. So this is one problem. Another problem that leads to a similar thing is the problem of an antenna array which records radiations from various locations from k various sources. Now when you have this thing, the received signal is also written as a of theta 1 theta 2 theta k, where a of theta is characterizing the response of this array of sensors to signals impinging on them from the various locations in space, okay? So imagine that the space is parameterized by this theta, okay? So now you have an array manifold. This is called the array manifold. And here too we want to recover the thetas. And here also we can rewrite the problem as a very, very, very large matrix A displaying the array manifold and a vector which has very few entries which are different from 0. Okay? So again, sparsity is coming in this problem, although it was not presented in the beginning as a sparsity problem. So the matrix A obeys, from physically constrained, obeys a lot of nice and good properties. So in 1979, while I was at Stanford, this gentleman by the name of Ralph Schmidt came up with an algorithm to do recovery of signals from this in this context, and it's called the multiple signal characterization algorithm. And it's in fact an algorithm that just says use the eigenstructure of the received vector, and the eigenstructure has n minus chi is a matrix which has n minus k eigenvalues which are small, which correspond to the noise, and so forth and so forth. I don't expect you to follow this and to look at the entire development, but you can use the eigenstructure of this autocorrelation matrix in order to pick out in a nice way by using some kind of a linear search, pick out the right locations of the non-zero elements in this solution matrix. And this is a very wonderful algorithm. Actually, probably Ralph Schmidt's music has zillions of citations by now, because it is a very, very important and very interesting algorithm for recovering signals that have a certain model, okay? And the model is that it's a sparse signal in some representation, okay? Okay, so this is wonderful, but it's not so good, because what we need in this solution, we need the autocorrelation of the signal, which means we need lots of repeated versions, random repeated versions of the received signal. But what happens if we have only one response vector, and in the sparsity problem that I defined first, which is solving a matrix equation which is underdetermined, it is the case that we only have a big matrix, and we have a huge vector who is only a small number of entries. So the question is, what do we do when we have only one response? Okay, so we sent this signal into the medium, and we got only one response. So engineers have known for many, many years what to do in this case. Engineers who dealt with radar signals have solved this problem for us. What was their engineering solution? Are there some engineers here in the is there somebody who is a real engineer who knows, who learned about what is called matched filtering? Unzer knows. Matched filtering. So what is this? In the echoes example, the radar engineers are taught to use the optimal matched filter. This filter correlates R with A of t minus theta at various locations, and it picks up the locations where this thing is high. So let's just emulate what they are doing. So let's take this idea, and in fact we can do the following. We can take for all theta, we can compute the inner product between R and A of theta, and this will be a function of theta, and you select the k maximal locations, presumably because that's where the signals were, and when you have matching you get local maxima. This is a very nice solution, and this was shown in various engineering courses to be the best. Well, it is called in sparsity today, by those who never learned about matched filters, it is called the thresholding algorithm. Okay, it is an algorithm in the sparsity literature, but many people would not know that this is just what they are just applying is they are applying a matched filter. Another method that you could do is the following. You could compute this R of A of theta and select the maximal value, and then subtract the corresponding part. So subtract the corresponding projection from R and multiply it with A of theta in order to get the next R next, for which you are going to proceed exactly in the same way, and you peel off one by one these maxima. You don't search for the k maxima all at once. And this is also a method that is being used in sparsity, and it is called the matching pursuit algorithm by some people who probably knew about radar echolocation. Okay, so now what we have is both the echo resolution and direction arrival. We can lead to the following problem. So we know how to solve such problems, but we can so in both cases what we want is we want to find an x so that ax equals to r and j0 is less than k. This is the sparsity constraint, or this is the noisy case, and we know that such problems can be solved nicely and efficiently and so forth. Now we could prefer a variational approach, and we could also write that we want to minimize the one norm of x and multiply it by r minus this. This is exactly the same problem as above. But now if we write it in the continuous case, you are going to see this formulation. So what is this formulation? This formulation, I claim, is an over-parametrized version of the variational problem that I talked about. This is the thing that says that x theta should be smooth, and this is the thing that says that the received signal should be close to the data that you are actually. The data should be close to what you think the signal should be. Now let's look at the classical, the continuous case variational problem that I talked to you. In fact, is very close to the Rudin-Osher-Fatemi framework, in which we are given a noisy signal. So here assume that you are given a noisy signal, which is some desired signal m and some noise. And what you do is you want to recover m, and therefore you are going to minimize over all possible m's of the closeness. This is the distance between the received signal and the candidate for your optimization, for your minimization, plus lambda times, and this is the smoothness prior, okay? So now let's do the following exercise. Let's do this and write this in a slightly different way by rewriting m of t as an integral between 0 and t of the m derivative of theta d theta, and then the entire expression here is written in terms of the derivative of m of t. Okay? And then now you can write a of t theta. You can define a of t theta as a function which is 0 between which is 0 up to 0. Then at 0 it jumps to 1, and it stays at 1 up to the moment t, and it goes to 0 again. This is it's a function of theta, but it has this parameter t of the location where it goes down. So now you agree with me that this can be rewritten as the integration over the entire domain of a of t theta m of t, because this is just 1 at the right locations. Okay? So now we have this expression. Remember that a of t of theta can now be regarded as that column, the columns of the A matrix. So now rewritten in terms of the derivative of x of theta, which is the derivative of d theta, this is what we have. And in the discrete case, this is what we have. And now look what we are having. We are having a matrix A, AX plus n. It's exactly of the form that we want. Now this circle of ideas leads to the following interesting way of defining an over-parametrized model. So let's take the most basic over-parametrized model that we could think about. We could think about m of t as having the following model. It is a superposition of phi t's, which are given functions. These phi t's are given functions. They are functions that we know. They are in a repertoire of possible functions that we are going to now mix and match. And how we are going to mix them? We are going to mix them by xi's, and xi's should be constant, but they are not constant. They are varying with time. Okay? Now you might say that this is too loose a model because you can put a lot of things in it, but but we assume that from the real life we have these phi i's, and the xi's are just coefficient functions that we usually have, that they are piecewise constant. Now we observe this m of t with additive noise, and we want to recover m of t, or in fact we want to recover these xi's of t from r of t. Okay? So we have defined now in this game we have defined now the xi of t's, the xi of t's are in fact these ABCs that I was talking about in the beginning. Okay? So this is where we are. And now the variational approach for this would be, natural, would be to write up psi, a variational functional, which is r minus the sum of this, plus something that measures the goodness of fit of these xi t's to our model. But notice, what do we know really about these xi's? About these xi's, we know that they are piecewise constant. Okay? So the question is, how do we really account for this knowledge in this second term of the what is called the regularization term, of the second term of the optimization? Well, it's very difficult to account for piecewise constantness. Okay, that's not something for which we have a standard measure. Now, what happened is that we can get very good results of denoising, and we did for many examples, but we did not have a good estimation for the xi functions. Okay? The xi functions were not, so you can go ahead and do the gradient descent and do whatever you know how to do for such functions. For example, with this term in which you sum over the interval of the integrations of the derivatives, but you don't get, you get a good result in terms of recovering a good m function, but you don't get the xi's correctly. You don't get what we would like mostly is, we would like mostly the segmentation of the signal into these portions where the coefficients were constant. That's a segmentation problem, and this is exactly what we observed with the optic flow method. The optic flow method gave us a very good result in terms of getting good optic flows, but it didn't give us a good segmentation of the images in terms of rigid objects. Okay? Why? Because the optimization, as it was written in this blue expression here, or some penalty encouraging piecewise constant, but this we were told by the ROF people, these were told that encourages piecewise constant, but it does a horrible thing of segmenting it into many more segments, and they are not correlated and all these things. So we didn't get the right piecewise constant result. So the Euler-Lagrange does a good job, but it's not in recovering the piecewise constant thing. So it's here that the new approach had to come in, and the new approach had to come in based on optimizations using sparsity priors, using sparsity in a fundamental way. And what it is, so let's look at the very simple discrete time example of a signal which is piecewise linear. Okay? When a signal is piecewise linear, it can be written as a combination of one of two functions, two standard functions, the one function, the function which is 1, and the function which is t. Okay? everything is a times t plus b. Yes, so it's everything is a combination of a constant and the t function. So now write m of t as 1 times x of x1 of t plus t times x2 of t, and x1 and x2 are jointly piecewise constant, and they change at the same location. Okay? So now in the discrete case, let's rewrite this, and when you rewrite this, you have an expression like this, and now you have to add plus lambda, a penalty term that makes the vectors piecewise constant and changing in unison. Okay? So apparently it's the same problem that we have encountered before. How do you actually make this do? So let's write the first one as r. This is just a rewriting of that expression, and then this is the question of the $1,000,000 question. How do we actually do it? Well, the vectors delta xi and delta x1 and delta x2 can be written in the following way, and therefore x1 and x2 can be written as something that is a lower triangular matrix of ones times these deltas. And now what we can do is we can write explicitly when we do this when we write these deltas, we write lambda times d1 d1 plus d2 d2 inner product. This is what we are this is a term that enforces the joint sparsity pattern of the delta x1 and delta x2. Okay? So in this form, the optimization is what is called a structured sparsity problem of an almost standard type. So why is it almost standard type? Because now there has been so much work in sparsity that people have actually addressed this problem. And then Raja and Michaelad and myself, we tested several cases of 1D and 2D piecewise linear planar fitting problems with this approach. What happens is that this approach, the explicit use of sparsity-based variational methods in order to impose the sparsity, the piecewise constantness of the coefficients, has actually gave us very good segmentations, and actually it was reported. So let's look at some examples that this 1D signal provided us. And I tell you, the whole 1D case is just an example to show you how things might work out and how things should work out. And there is a lot of more work that is needed in generalizing it to many more complicated cases. But here is the problem. So this is a signal G, which happens to be this piecewise constant signal and the noise. The noise is rather large, and you cannot expect to see the perfect locations of the breakpoints in this linear signal. So this is exactly following the procedure that I showed. So here is the sparsity-based solution. So what you have is you write down these things. You have k, define k, the number of jumps that you expect, and you can take k as an upper bound of how many jumps you have. Then you define this problem, which is the sparsity-based optimization problem, and then if k is unknown but the noise energy is known, then you can solve others. And this problem has been treated in the sparsity literature, and there is an algorithm that deals with it, and this is what you get. So you get the line fitting experiments, you get the results, the recovery results. Now notice that these jumps are due to the fact that there is nothing in the procedure to enforce continuity. Okay, we didn't impose continuity. However, you could impose continuity. However, what you get is you get the locations, and these are the locations where the jumps in the various parameters are. You can see them because these are the piecewise constant parameters. So if you want to solve the jumps problem, you just add the condition that wherever one portion ends, the second portion gets just the continuation of it. So you add the condition combining the left and right parameters, which reduces the search space, and you get such results, which are, in our opinion, quite nice and reasonable. So you can solve it. So you can go from 1D to 2D, and this is important for images. And you can do, you can consider the sparsity with respect to horizontal and vertical, vertical derivatives and diagonal derivatives in order to match shapes which have all kinds of directions. And actually, here you should extend to more directional derivatives as you wish. And you can have denoising examples. So you get with the standard one, you get this recovery. With the diagonal, you get a slightly better recovery, and here are the results that you get with the ROF scheme. And you can see the influence of these diagonals on the result. And here you get denoising for some standard images, and you get here the gradient map. And everything is, of course, not perfect, but you get segmentations, and you get geometrical in-paintings, and all kinds of examples. You see, when you assume the derivatives only horizontal and vertical, this is the in-painting that you get when you do directional derivatives. You get there, and you'd improve it if you'd get more directional derivatives. And these are just initial results, but they sort of show you that there is a future in this piecewise constant over-parametrization idea, and the future is dependent on having good terms here that enforce behavior according to the piecewise constant model, if that is your model. But your model might be piecewise more complex models, and then you'd have to do sparsity in a higher order derivative of some sort. But the question is, how do you actually design your variational problem? That is very important. So, as I told you in the beginning, my aim is not to provide you a complete picture, but to sort of try to convince you that you should look at over-parametrized problems, in spite of the fact that sometimes the idea might seem crazy, and I encourage you to try to do something with it. Thank you very much. So now it's time for question, comments, remarks. Nobody's attacking the idea? Mikhail, say something. Say something.
Okay, so I guess when you look at your piecewise constant or linear, I think, I mean, can also be tackled using different basis functions like splines L1.
Yeah. Okay, so yeah, I encourage you, splines. Everything is done by splines. Yeah.
So it relates to.
No. So you could imagine, but what I want is I want people to adopt the idea. You know, we have models for signals, so you should go ahead and exploit the models.
And then, okay, so since you challenge me,
yeah, I know, of course I challenge you.
So why don't you explicitly put that your variables, they are, in fact, they're like indicator functions?
But can you if your variables are multiplied by indicator functions or by step functions, can you deal with them? Do you know what to do then?
Because you can use things like Viterbi algorithm, dynamic programming.
Oh, okay. But that's exactly the message of the sparsity. That's exactly the message in the sparsity. Okay, so you press the thing exactly where it should. Yeah. So that's the message. But I think this idea is worth paying more attention to. Okay.
Any other comments or remarks? So for the 1D signals, you have many pieces of piecewise linear. So you have several A's and B. Can you explain more in detail how do you compute those?
Excuse me?
Like these. Yeah. And then you have one piece, you have one A, one B.
Yeah.
You have different A and B's.
Yeah.
So can you explain a little more how do you compute it?
Well, it comes out from the algorithm. The algorithm gives you, and what is nice is that what I was, you know, the ROF. It is said in the literature that ROF is giving you piecewise constant things. Okay, but it gives you a very strong fragmentation at many locations because the optimization desires that. Okay, here what we have is we impose sparsity, so we don't allow too many changes to happen, and we impose the fact that the two should change at exactly the same location. So the change happens in the vector A and B. Okay, so there are few locations, and I'm not allowing A to change without B. B will change at exactly the same locations, and B cannot change. When one of them changes, it accounts for a double change, and therefore sparsity will not allow you to do a change in B, a change in A, and not in locations which are not necessary by the two of them. And this gives very nice results.
So if it's a piece of quadratic, you just increase one operand. Right?
Yeah, exactly. Yes.
One quick question. So is it really due to the change from L1 to L0, or you could also have a joint?
It's not due to so much to the change from L1 to L0. It is due to the fact that the sparsity requirement is ingrained, is put in these algorithms. So there is a strong request. Yeah, but L1 only is not the answer, because L1 is the ROF. L1 is ROF. ROF is L1, and ROF is leading to too many. So you have to do L1, but penalize many jumps. Okay, so somehow, and somehow we didn't know for a lot of time. We didn't know how to put in the penalty for many jumps, and sparsity does it for you. Sparsity, you know, it tells you you are allowed k jumps. Okay. Thank you.
Other comments or remarks?
Thank you. Gabriela? No? Thank you.
Okay, thank you.
Thank you.